Hi everyone. I wanted to go over a little more detail, something about the mechanisms we've met. Okay, so we've been looking at the electrophilic addition mechanisms for alkenes, and in them we've formed carbocations. So I've brought my models with me again. And let's say that I've got propene wanting to react with hydrogen bromide. So hydrogen is the white and green for the bromine. So the reaction that we've met involves the carbon-to-carbon double bond breaking so that a pair of electrons can be donated to the delta positive hydrogen. So we're going to break that. We're going to, I can do this, make sure you can see the whole thing. Put the hydrogen on here. So I've got a new bond to hydrogen in the molecule there. And the bromine atom, which of course is now a bromine ion, that's representing a pair of electrons. Pair of electrons there, and a carbon atom here, which is missing a pair of electrons. It's only got 3 things bonded to it. Don't be tempted to confuse this with a free radical that would have 1 electron there, ready to bond to something else. This has 2 electrons missing. Okay, it hasn't got 1 unpaired electron, it's got no electrons sitting there, and it's got a positive charge. So this is the carbocation. The new electrons, which will draw as a lone pair on the bromide, are going to come towards that and complete the reaction, like what we had with the curly arrows. So, the thing I want to talk about today is this stage. So this mechanism, unlike the haloalkanes one, this mechanism has what we call an intermediate. We meet intermediates in organic chemistry. They're things that exist, that are usually quite reactive, that happen, as their name suggests, midway in a transformation, midway between other things. And you'd usually get a mark in the mechanism for the intermediate, for having that drawn correctly. So here's our carbocation, and that formed from the bond breaking. So our double bond broke. We donate electrons to this hydrogen here, and we represented the bond as breaking out towards this. We broke it that way. So if you've seen me draw mechanisms, I tend to draw them showing that specifically, showing which direction they were going in, so that I can remind myself which one I've shown it going towards. So that way, as you look at it, it's towards the right of the screen. However, the bond could also have broken towards the left of the screen. That bond could have broken there, and the 2 electrons flown around. Flown isn't quite a technical term. If the bromine and the hydrogen were over here instead, could have been hovering here. I don't know how well you can see that. Could have been hovering nearer this carbon, broken out towards the left, and formed the bond there. So that would give us the hydrogen here, and the positive carbon atom there. So that's a different intermediate. This intermediate is different to this one. And they differ by which carbon has the positive charge on it and which one's bonded to the first atom from the electrophile. So, there is a rule here you need to know. We're more likely to form this carbocation than this one. Okay? So this is less likely. That is because this carbocation is not stable. As I said, it's an intermediate, it's unstable, it doesn't like being unstable. You've met that a lot of times. If things are unstable, they want to react and form something new. So this wants to, well, we won't worry too much about what happens next, but it doesn't want to exist, basically. And the more likely it is to exist, the more likely the reaction will happen in the way that forms it. Okay? So if this is the preferred carbocation, then the reaction will form this one instead of forming the alternative. So this is called a secondary carbocation. I can give this family of things like this a label, secondary carbocation. And it's secondary as opposed to primary or tertiary because I can look at how many carbons this carbon's bonded to. So if I know it's a carbocation, I look for the carbon with the positive charge, which also means the one with only 3 bonds, and I count how many carbon atoms is it bonded to. 1, 2. Secondary. As a secondary carbocation, it's got 2 sets of bonds like these nearby. So every carbon atom it's bonded to can help make it more stable. There's what we call an inductive effect. Inductive is it's sort of transferring or moving. There's an inductive effect of the electrons in this bond moving towards that positive charge. Now these electrons of course are negative, and if that's positive they help to you can think of it as relieving the positive charge. They make it more stable by donating electrons in that direction towards the carbon atom. And again, the ones in this carbon to carbon bond do the same. The ones in the carbon to hydrogen bond don't. So this carbocation, the secondary one, has 2 carbon atoms donating electrons towards it, making it more stable. So that's the more stable carbocation. Our alternative, in which we had this, well, if that was secondary, with 2 carbon atoms bonded to it, this one would be primary, only 1 carbon bonded to it, and 2 hydrogens. So there's only 1 carbon making this more stable. There's only 1 set of electrons coming towards that positive charge with the inductive effect. So that is a less stable carbocation. The less stable the carbocation, the less likely it is to form. So it's unlikely we're going to get to this stage, which means it's unlikely we're going to get to this final product. So that is called the minor product. Some of it will be made, maybe between 1 and 5% of each molecule will end up looking like this. Some of it will be made, but it's the minor product. So, unsurprisingly, the more stable one will lead to the major product. That's the more stable carbocation. That is the more stable. That is the major product. More stable carbocation, major product. Okay? And of course, there's one more option. If I try a different molecule, I will reset it just so you can see it again. If I try reacting hydrogen bromide with methyl pentene, this time I've got 2 options. I've got a less stable primary carbocation. That would lead to the minor product. Okay, that would lead me to the minor because it's less stable. And a more stable, you might have worked this out already, a more stable tertiary carbocation. There's the carbon with 3 other carbons and 3 sets of bonds that can do the inductive effect towards it. Okay, so that's a tertiary. And then I'd end up with that as my overall product. Okay, so that's a common question to be asked about a mechanism. Justify why this is the major product, this is the minor product. And it's a classic quality of language one. Students often lose this mark because they use the word it, which we don't like to see in exams. We don't like to see it is more stable. Okay? If asked why this is the major product, you would need to say it's the major product because it is formed via the more stable tertiary carbocation. Via meaning the route that got us there included the tertiary carbocation. If you looked at this and said, this is a tertiary carbocation, it's more stable, you wouldn't get the mark. So the more stable one, it is formed via the major product is formed via the more stable tertiary carbocation. Okay?